Hello everyone, this is Mr. 13 Things, following up on the discussion of understanding what the values of the unit circle are for the major, let's see how this works. I go backwards, for the major points on the first half of the first quadrant. And so I'm going to draft those there. I'm going to kind of, right, the unit circle, remember, it has a radius equal to 1, a diameter equal to 2, an area equal to pi, and an angle equal to 2 pi. So we're going to look at the first half of the first quadrant. We have angles here, a point there and point there. That's 45 degrees, right? This is up here. This is a point there. So we know the coordinates of that are 1 and 0. The coordinates of that are 0 and 1. And we know at 45 degrees, the coordinates of the square root of 2 over 2 and the square root of 2 over 2. We know then at 30 degrees, someplace there, the coordinates are more x than y, the square root of 3 over 2 and 1/2. And then finally at a point there, trying to draw the circle around here, a point there at 15 degrees, we know it's a little bit more odd. It's a 2, 4, 6 square root with a plus, and a 2, 4, 6 square root with a minus. Once again, knowing that the x is more than the y. So you see all that, but then what are these numbers? What do they mean? What is a square root? And eventually you should know it geometrically, and we're going to do that right now for as many of these as we can. So we're going to draw the unit circle. It's not too bad. And we're going to basically think about something here with a length of 1. And something there with a length of 1. And so what in fact is the square root of 2? I'll go ahead and change the color. The square root of 2 is basically that length. So if this is 1 and this is 1, this here is the square root of 2. So now you know what the square root of 2 is, and later on you can think about making boxes and doing sketches and playing around with this, but that's the square root of 2. So then what's the square root of 3? Square root of 3, what we're going to do is we're going to go ahead and remember that we do a little playing around on this circle. We divide that in half and we divide that in half, and this point there is at 60 degrees. And we also have this concept of the vertical line coming out here, that if we take a line through here and extend it up, that's called the secant line basically. This here is called the tangent line. And this tangent line has a length of, you guessed it, the square root of 3. And so if you think about it, the square root of 3 is going to be square root of half of that is, square root of 3 over 2 is going to be half of that. So you now know what the square root of 2 is and the square root of 3. The square root of 6 we're not going to get to. Though in fact it turns out to be the square root of 3 times the square root of 2 equals the square root of 6. That in fact is true. Let's see if that's about right. Square root of 3 is a little bit more than 1. Square root of 1, that should be about right. Square root of 3 equals, you could do this because you could also go backwards from the square root of 6 equals the square root of 3 times 2, and then you could break things up. The square root of 3 times the square root of 2. So you can see later on that really when you get to area relationships, you take this length times that length and you get the square root of 6. So you can see where the square root of 6 comes in some way, shape, or form. I want to go now and review this. I'm going to go ahead and erase all these things if I can and just look at how we completely finish out the construction so we get back to our edit, cut, to all of our values, important values from this construction. I'll try it one more time again. I'm going to draft the unit circle here. And we want to remember that we not only want to get square root of 2, square root of 3, but also square root of 5 and phi. So let's think about this. We'll do it the first one in green. If not, edit, undo, grab the green up here. That length there, the square root of 2. If you take this in your eye, this length right up here, with a 60-degree line coming out, is the square root of 3. Now what I'm going to do now is fill in the black. Now we're going to come upon how to get the square root of 5. So what we're going to do is we're going to come down and square out this circle, or this square, which is 1 by 1. We are now going to basically draw an arc and bring it down to here. So we're taking that arc from there and we're swinging it down to here. This value here turns out to be the square root of, something called phi, or the golden ratio. So now we have this value here, and what we're going to do is we're going to continue this line out here, and if we extend from that point, which is 1, through there and take it to there, this length here is the square root of 5. So in one construction you can get the square root of 2, the square root of 3, the square root of 5, and then back to this relationship and rate. Important thing to know is that when you write this, phi, or the golden ratio, is in fact the average of 1 and the square root of 5. And you can see that now geographically, or geometrically, what that is. So as students kind of play around back and forth looking at numbers, irrational numbers, they can start to realize that they are in fact, right? They are in fact pictures on a values of lengths on a standard construction, and soon they will learn that the tangent of 60 degrees, the tangent of 60 degrees equals the square root of 3, which means the tangent of 30 degrees equals 1 over the square root of 3, which they'll later see as the square root of 3 over 3, because mathematicians don't seem to like the radicals in the basement. That's only okay in Madison, I guess. So this sense that you can get a construction for the square root of 2, the square root of 3, and the square root of 5 very quickly by playing around with some basic geometry is worth knowing, so that students don't basically mystify the fact that if they know, I'm going to do the angles here, angle of 0, pi over 12, pi over 6, and pi over 4. And if they want to know the cosine and the sine, knowing that the cosine is 1 and the sine is 0 because this is the x and the y value, here it's 6 plus, it's the pattern again, square root of 6 plus square root of 2 over 4, and this is the square root of 6 minus the square root of 2 over 4. Now again, that idea of what is the square root of 6 is a little bit tougher because you've got to think about an area defined by this length and that length, but it is conceptually reasonable. For 30 degrees, remembering that it's more x than y, the square root of 3 over 2, and then 1/2, 1 being the square root of 1. And then for the pi over 4, the square root of 2 over 2, the square root of 2 over 2. And tying these things back to a picture based on a unit circle where the radius equals 1, the diameter equals 2, the area equals pi, and the angle equals 2 pi, over and over and over again until it becomes as rote, if you would, as 2 plus 2 equals 4, or 4 divided by 2 equals 2, or 6 times 3 equals 18, etc., etc. Square root of 2, Pythagorean's number. Square root of 3, the tangent of 60 degrees. Square root of 5 coming from this construction of 1 and phi, where phi is equal to the average of 1 and the square root of 5. This, of course, is also equal to the ratio of the two numbers in the Fibonacci series beyond the 13th term. And the best one to know is, I think, 610 divided by 377. That's coming from 89, and then 144, 233, 377, 610. If you take the ratio of one to the other, you essentially get that number as well. Thanks for listening.